Suppose there's a relationship between two random variables x and y. In that case, knowledge about the value of y may lead you to reassess probabilities involving the random variable x. For example, suppose that we flip two fair coins and that yi is equal to 1 if the ith coin lands heads and that y is equal to 0 if it lands tails. Let us define x to be the sum of the two y's. X is equal to y1 plus y2. In that case, the probability mass function of x is as follows. The probability that x is equal to 0, the probability that x is equal to 0 is the probability that both coins land tails, which is a half times a half, which is 0.25. In the same way, the probability that x is equal to 1 is the probability that exactly one of the two coins lands heads and the other tails, and that is 0.5, and the probability that x is equal to 2 is 0.25 also. Suppose now, however, that we are given some additional information, e.g. that we know that the first coin lands heads. In that case, we have to reassess the probabilities. In this case, the probability that x is equal to 0 is 0, because x cannot be less than 1 if y1 is equal to 1. The probability that x is equal to 1 is now the probability that the second coin lands tails, and that is a half. Whereas the probability that x is equal to 2 is the probability that the second coin lands heads, and that is a half also. Notice that the random variable x hasn't actually changed, it's just our assessments of the probabilities involving x. 0.25, 0.5, 0.25 has been reassessed to become 0, 0.5 and 0.5 on the basis of the new information about the random variable y1. As before, we consider discrete and continuous distributions separately. Suppose first that x and y are discrete random variables with a joint probability mass function fxy and marginal PMFs fx, fy. Then by definition of conditional probability, we have that the probability that capital X is equal to little x, given that capital Y is equal to little y, is this ratio over here. The numerator is just the joint PMF of x and y, and the denominator is the marginal PMF of y. Hence, we define the conditional PMF of x, given that capital Y is equal to little y, to be this ratio as follows. If we take the denominator over to the left-hand side, this is often written as follows. The joint PMF is just the product of the conditional PMF with the marginal PMF. Next, we consider conditional distributions for continuous random variables. Suppose that x and y are continuous random variables, in which case they will have a joint PDF denoted by fxy. We will denote their conditional PDF as follows. The intuition here is that the conditional PDF, given that capital Y is equal to little y, times dx, is approximately equal to the probability that capital X lies between x and x plus dx, given that capital Y lies between y and y plus dy. By definition of conditional probability, that can be expressed as this ratio, and the numerator is approximated by the joint density times dx times dy, whereas the denominator is approximated by the marginal density of y times dy. The dy's cancel out, and that leaves us with this. In that case, we can cancel the dx's as well, and so we define the conditional density of x given y in the same way that we defined the conditional mass function on the previous slide, namely the joint density divided by the marginal density. Up to now, we've used the notion of independence of random variables in a rather informal sense. We can now make this definition precise. Two random variables x and y are said to be independent if and only if the event that x belongs to A and the event that y belongs to B are two independent events for any two subsets A and B of the reals. By definition of independence of events, this simply means that the probability that x belongs to A and y belongs to B splits as a product of the probability that x belongs to A and the probability that y belongs to B. In terms of conditional probabilities, this means that the conditional probability that x belongs to A given that y belongs to B, which by definition is given by this ratio, is just equal to the probability that x belongs to A, because the numerator here splits as a product, and therefore the probabilities that y belongs to B cancels out. Intuitively, this means that information about y does not cause us to reassess the probabilities involving x. In other words, the conditional probability that x belongs to A is the same as the original probability that x belongs to A, conditional on no information. In some sense, therefore, knowledge about y tells us nothing new about x. We use this symbol here to denote independence. Now it can be shown that two random variables x and y are independent if and only if their joint CDF factors as a product of marginal CDFs. One direction here is very easy. The joint CDF is simply given by this. This event here is the event that x belongs to the interval from -infinity to x. This event here is the event that y belongs to the interval from -infinity to y. And hence this splits. Now the first factor is just the marginal CDF of x, and the second factor is the marginal CDF of y. And thus the joint CDF splits into a product of marginals. The same kind of reasoning shows that x and y are independent if and only if their joint PMF factors as a product of marginal PMFs in the discrete case, or if their joint PDF factors as a product of marginal PDFs in the continuous case.